Good morning, pre-cal. Today we're going to continue on to the next type of conic section. Last week we talked about the parabola. Today we are going to talk about the ellipse. And the ellipse, I guess as we know it any other time, we'd call it an oval, but the mathematical term for it is an ellipse. And we see ellipses most often when we talk about the galaxy, and that's the path that the planets travel. It's kind of an oval path. Here is the very wordy definition for an ellipse. And it's a little, it's a lot, is what it is. An ellipse is a set of all points in a plane whose distance from two fixed sums in the plane have a constant sum. So here are these 2 points, which are called the focus, or plural is the foci. So here's a piece of, well, it's a piece of rubber band. So what this is saying is, here's my 2 fingers, and it's on the focus. So I'm going to take my pen, and I'm going to draw, well, that's one way. Then if I moved it down here, I could, whoops, well, you get the idea. I'm butchering this. So you kind of get the idea that that's an oval, because the sum of the distance from 2 fixed points. So this piece of rubber band is only so long. So if I pulled it this way, I'm still adding my 2 pieces, and then any points on here, I'm just adding my 2 pieces. So that's how we come up with an ellipse. So these 2 points, those are the fixed points. My fingers didn't move. Those are called the foci. The line through the foci is called the focal axis. The point on the focal axis midway between the foci is the center. And the points where the ellipse intercept its axis are the vertices. So here's one vertex, here's the other vertex. So center, 2 foci, 2 vertices. Now this one is, gosh, I forget what these are called. I want to say these are called the, this is the major axis. Different books handle it differently. Really, I do know, but I don't remember what this book does per se. And this is called, if this is the major axis, this one is the minor axis. So let's see, let's go on. I'm going to put these notes on Google Classroom, so we have those to look back at as well. So this is pretty much what I just drew. Here's the focal axis. That's also the major axis. So focal axis is the same thing as major axis. Now if they use the term semi-major axis, a semicircle is half of a circle, so this would be the semi-major axis. So from the center to the vertex would be the semi-major axis. This is on your formula sheet. This is on your formula sheet. Now there's something I want to draw your attention to here, and this is way up here. So first of all, we've got 2 different orientations we can have. We can have it along the horizontal, so the oval, the oval is kind of an elongated part. If the elongated part is on the horizontal, we've got x squared over a squared plus y squared over b squared equals 1. Ellipses always equal 1, and they're always a sum. If it's elongated vertically, it's x squared over b squared plus y squared over x squared equals 1. Now how do we know which one's which? Right up here. A squared is always the largest. So if a squared is underneath x squared, we know that the horizontal, whether it's the actual x-axis or parallel to the x-axis, we know that it's going to have a horizontal. It's going to be elongated horizontally. And if it's a squared is under the y squared, that means it's elongated vertically. And the other thing we have is we call this the Pythagorean relation. The Pythagorean relation. And so if we look at this drawing, so here's our foci, and notice from the center to the foci, that's C. From the center to a vertex is A, and from the center to the vertex on the minor axis, that's B. So there's our A, our B, and our C, and there's the Pythagorean relation. Notice I didn't say theorem, the Pythagorean relation. But we need to remember these 2 things that I've highlighted. All right, so this is on your paper, so we're good to go there. We already talked about that. Well, this is the Pythagorean relation then. So if we, let's see, we've got c squared equals a squared minus b squared. So if you look at it, c squared equals a squared minus, so a squared is always going to be the largest, minus b squared equals c squared. Okay, this is what you need to remember. I guess don't have to deal so much with that. Oh, a problem. Find the vertices and the foci of the ellipse 9x squared plus 4y squared equals 36. Well, the first thing you notice is that it is not in this form. So we need to get it in this form. It has to equal 1. So let's make this equal 1. Divide everything by 36. X squared, 9 divided by, or 436 divided by 9 is 4. 36 divided by 4 is 9. And equals 1. So 9 is bigger than 4, therefore it's going to be elongated vertically. So I know that 9 equals a squared, so a must equal 3. I know that 4 must equal b squared, so b equals 2. Now do a quick sketch of this. It's also centered at 0, 0, so there's my center at the origin. A is the major axis, so up 3 units, over 0 up 3 is one vertex, over 0 down 3 is the other vertex. So, and let's see, this is 2, so out 2 is the this would be the semi-major vertex, and the other the other side, or minor would be out here. So this is -2 and +2. Okay, I just butchered that, but you get the idea. Now we have to figure out where the foci are. So let's go back and look at our Pythagorean relation here. C squared equals a squared minus b squared. So c squared equals 5, c equals the square root of 5. So from the center, if I go up the square root of 5, and if I go down the square root of 5, I'm going to find my foci. So my vertices are going to be at 0, comma, plus or minus 3. My foci is going to be at 0, plus or minus the square root of 5. This can get complicated. We're not going to get that complicated in this circumstance. Oh, this just says that I'm right. 0 plus or minus 3, 0 plus or minus the square root of 5. Yep. Oh, another problem. Find an equation of the ellipse with a foci of plus or minus 2 whose minor axis has a length of 2. Well, first of all, we have to find the center. And the center is right in the middle of the two foci. So here is a focus at -2, 0, and this is +2, 0. So between -2 and +2, halfway in between is going to be 0. So I know that my center is at the origin. So center is 0, 0. And remember that foci, that's C. So -2, +2 from 0 is 2 units. So C equals 2. A minor axis has a length, let's do a sketch here, -2, 0, +2, 0. So there's my foci. There's my center. My minor axis, the entire length of my minor axis is 2. So that means one above and one below the origin. So, boom. Okay. So let's see. I've got B equals, let's see, if the entire minor axis is 2, that means B must equal 1. And then I've got C squared equals A squared minus B squared. So 4 equals A squared minus 1. 5 equals A squared. That means the square root of 5 equals A. So if I go over the square root of 5 and left the square root of 5, I'm going to get my vertices. Find the equation. Okay, so the first thing we have to do, oh, this is centered at the origin, so that's going to be easy. So I've got x squared plus y squared equals 1. And now I have to figure out what goes underneath each of these. Let's see, the bigger one has to be A, and it's elongated horizontally, so that's going to go under the x, so A squared is 5, and B squared is 1. So that's what I was looking for. This just says x squared over 5 plus y squared over 1. Yep, we were right. So if it's situated somewhere else, we have to accommodate that, and that's just the same thing that we did for parabolas. So if we pick up the center and move it over, well, that means the foci and the vertices are kind of picked up and over as well. Find the center, vertices, and foci of this ellipse. Well, the center is going to be at -1, 1. So that's my center. Now the bigger number is underneath the y, so that means it's elongated vertically. So -1, 1, there's my center. This says A equals 3 and B equals 2. So 3 units, -1, 1. So 3 units up is going to be my vertex. So -1 and then 3 units up from 1 is 4. -1 and 3 units down from 1 is -2. We don't really worry too much about that minor one. So there's my ellipse. We found the center. Our vertices are at -1, 4 and -1, -2. And our foci, let's say we have to do our Pythagorean relation. A squared equals 9 minus 4. C squared equals 5. C is the square root of 5. So our foci is going to be -1, and then this is just going to be ugly. We can't really make this any better. 1 plus the square root of 5, and -1, 1 minus the square root of 5. And I'm just going to leave it that way. And if we look here, -1, 4, -1, -2, and there's the square root of 5. Yeah, and they left it in that form as well. The last one to talk about, that's just an example of orbits. The last idea to talk about is this concept of eccentricity. Eccentricity. And what you really need to take away here is that A, B, and C, we know how we find all of those. This is the formula for eccentricity. And eccentricity simply means how not round, that's an odd way to put it, isn't it? How not round an object is. So a circle is very round, so it has an eccentricity of 0. A parabola is not round, so it has an eccentricity of 1. And in between 0 and 1 is the ellipse. Did I spell that right? No, I'm missing something. Yeah, that's right. An ellipse has an eccentricity greater than 0 but less than 1. So the eccentricity of an ellipse is C over A. So if I go back and if I find my last problem, C over A, whoops, A. So the eccentricity of this ellipse is the square root of 5 over 3, and that would be some sort of fraction, certainly less than 1. So an eccentricity is nothing more than just figuring out what C over A is. That's a lot, I know.